Some of you are getting to the point where you're almost ready to use these tools. I'm going to point out it's a great idea to sketch on top of your sketches when you come up with the radial vector force pairs. And so here you ask yourself a question you know the answer to, and so here's one for you. You have point loads at third point, so 10 down, 10 up, that means 10 at each reaction. What in fact would be the shear and the moment at the middle of the span if these things were all equal? Well, you know the shear has got to be 0 and the moment should be something equal to this force times this distance. How does that look like when you put it in the calculator using, and again they can be kind of, they need to be used in succession, VList 2, VList 3, and VList 4. And then actually also the A beam select for determining a required moment of inertia. Well, let's take a look at this. First off, let's understand that hopefully you need to then dig into these when they explode because they're not perfect. I'm going to run VList 2, and what that does, it turns out, it sets up my editor so I can now go ahead and put in all my radial force pairs. And you see there's a couple already in this calculator. So I'm going to put 0 here and 0 here. But let me put in all of my radial force pairs, realizing that in all reality very often you might need to kind of do some calculation for the reaction. So we have it 0 and 0. If we think about this as a force upwards of 10, and nothing in the x, at 6.66, if this is a 240 divided by 3 is 80. At 80 inches, 80 times 3 is 240. You got a force of minus 10. At 160 inches, you've got a force of minus 10. And then eventually in your last force at 240, remember you've got to have all the reactions kind of input for this actually to start working for you, and you need that as a positive 10. You now have each of your radial force pairs. You notice we're doing this as a flat, so you've got nothing in the Z. This will work for 3D, but you've got to be very cognizant. So you got 4 in a row. If you now hit second quit and go to program VList 2, what VList 2 does, it should calculate and give you that error. It is actually calculated, and the reason it's an error is that you have some things equal to 0. That's what you would actually expect. I'm going to hit clear here, change my mode just to double check that my float here is a little bit higher. Second quit. Now go to program VList 3. VList 3, you see that little pause there, and you hit that there, and it tells us what in fact we know that the sum of the moments is equal to 0. Now the last thing you need to do is realize when you go to second quit, when you go to program VList 4, you're going to get a little bit of an instruction there. The instruction is that you want to adjust your radial vectors and then also include a list called include I, where you set it at 0 if you want to ignore the force. So in this case, we're going to go ahead and hit clear or enter or clear, and we're going to want to do that. So let's say we want to calculate at this point the force or the reaction here at, maybe we said this was the middle 240 at 120. Well, what are we going to do? We're going to take and first adjust our radial x vector down by 120. We're going to shift our coordinate system, and then we're going to discount everything to the right of that. How do we do that? Well, we just say second list LRX, and you probably write a program to do this eventually. LRX minus my 120 is my shift, and I want to store it exactly correct into second list LRX. We've just shifted each of our LRX vectors 120. So if we look at them, that makes sense. This one, this. And then what you need to do is you need to actually go into the include INCL list, and you can do that by, I'll hit a clear here, going to stat, setup editor, and you want that to be second list, the include, I think that one's set in there, the include vector and the include list. You want to set that up so when you go to stat, edit, you can decide, yes, I want to include the first one and the second one, but not any of the other ones. I can now hear second quit. So I've done those two things requested. Now if I hit program vlist 4, it should actually calculate what is the moment. And if you think about that, if this was 10 and this was 120, we'll see whether this is actually correct. So this is, I'm sorry, this is 80, and so the moment indeed is 800. And you notice here the reactions are indeed correct. So that may seem like a lot of work when you've got, just 4 simple questions, because this in fact is, of course, a problem that you know the answer to. But in all reality, it is a worthwhile exercise if you have more and more and more forces where you can all of a sudden pick around in X, Y, and Z. I would recommend once you're done with any of this work like this, you still go back and reset, just like in terms when you do your coordinate system, your UCS is in AutoCAD. It's still not a bad idea to really switch everything back to the standard coordinate system. So to go ahead and say second list LRX plus 120 and store it into second list LRX. And you can write little snippets of programs to do this if you're going to be doing this on a regular basis. And now you see everything is back to where it would be. Again, that include variable, right? You might want to include all of them. So this basically, these are to show you how you would do these things in a spreadsheet. These would be just if statements. So that's how you go about using that one. I'll just show you. I'll hit a second quit here. I'll just run it, once again, run the program there. This time if I run it, everything should be included and everything is 0. So there is no reaction at the other side of the support. Now let me finally take you in the last couple of minutes to the program beam select and the inputs that were there. This is only it's not gonna select anything for you, but it's you enter Young's modulus, for instance, in steel it's 29,000 KSI. The equivalent uniform load in kips. So let's say on this beam here, 124 load, you had basically equivalent uniform load. Well, you had the total would be 20 coming down, and then it's a little bit more. It's probably in the order of 30. It's not twice as bad, but it's not spread out. Span in inches, 240. And deflection criteria, let's say you're going to use the deflection criteria of span over 480. This is going to get you a required moment of inertia to keep that deflection. And when you have that, basically you know that you're going to be deflecting at less than the span divided by 480. That divided by the half depth of the beam, let's say you were spanning 240 inches, which is 20. Let's say that was 6, would get you the section modulus that you would need. So remember that the section modulus is equal to the moment of inertia, second polar moment of the area divided by the half depth of the beam. So this would be a number that you can kind of plug through some tables or plug through some section modulus tables and select a beam for deflection. Once you grab that beam for deflection, you're pretty certain you're going to be okay, except in very long spans when it comes to deflection and stress, which is M over S. Okay, that's the introduction to these programs. These programs are all available, and they have a revision date of the 29th on them. Thanks for listening.